Thank you for stopping by this electronic poster of our pilot study of smartphone infrared pupillography and pupillometry. This is Omar Soliman, a former neuro-ophthalmology fellow at Wilmer Eye Institute and a current consultant neuro-ophthalmologist in Giza, Egypt. For disclosure, the custom-designed device described here is a pending patent for my co-authors and myself. The aim of this study was to describe and validate a novel custom-designed portable smartphone-based infrared pupillographer. The prototype custom-designed pocket infrared smartphone pupillographer device consisted of dual-synchronized camera module with two infrared mini-cameras, corresponding to the arrows in this figure, and a mini-infrared light source, corresponding to the arrow heads. When connected to a compatible smartphone, the two mini-cameras and the infrared light source are powered directly by the smartphone battery, without the need for external power supply. The smartphone camera complex can be either hand-carried, allowing for use at the bedside, or mounted on the slit lamp as in the figure on your right-hand side for optimal video recording stabilization. After connection with a compatible Samsung smartphone, infrared video and photo pupillography were attempted on 12 patients with different pupillary examination findings. Welch-Allyn halogen fiber optic transilluminator was used to test for pupillary light reflex and to obtain pupillary size snapshots in light. Captured pupillography media files were replayed on the smartphone by 3 masked ophthalmologists, and the agreement between their qualitative clinical evaluation was tested against the evaluation of the neuro-ophthalmologist who performed the real-time examination. Quantitative measurements of the pupillary diameter were performed by 3 investigators on 3 different smartphones using a custom-designed smartphone application, and using a Windows computer application on a desktop computer. This figure shows the interface of the custom-designed pupil gauge application, which allows immediate post-recording measurement of the pupil diameter. The examiner needs to align 4 vertical bars with the corresponding margins of the pupil and the limbus of the tested eye on the smartphone's touch screen. Then the pupillary diameter can be directly calculated as a percentage of white-to-white diameter of the corresponding eye, or in millimeters based on a fixed consideration of 12 millimeters horizontal corneal diameter for each eye. Infrared video pupillography of high quality was successfully captured for light and near pupillary reflexes, and infrared still photographs were obtained in light and dark conditions in 23 eyes of the 12 patients. Examination findings included relative afferent pupillary defect, normal pupillary examination, anisocoria, and relative afferent pupillary reflex by reverse. There was 100% agreement in the qualitative pupillary evaluation of the masked investigators compared with real-time clinical examination. The next 3 slides show 3 different infrared video pupillography recordings demonstrating left relative afferent pupillary defect, right afferent pupillary defect by reverse, and a normal swinging flashlight pupillary reaction respectively. Note difference in the stability of the video pupillography recording when the device is mounted on slit lamp as in the first video compared to when it is hand-carried as in the next 2 videos. Quantitative measurements of pupillary size obtained on the smartphone and desktop computer showed excellent agreement among the 3 investigators, with intraclass correlation coefficient ranging 0.98 to 0.99 and 0.995 for the smartphone and the desktop computer groups, respectively, which were statistically significant. This Bland-Altman plot shows excellent agreement between smartphone and desktop-based measurements of pupillary diameter with a level of agreement ranging between 0.27 to 0.32. Mean pupil diameter errors were 0.03 plus or minus 0.15 mm between groups. Various methods of smartphone pupillography and pupillometry have been described, each with its own limitations. In this table and the next 3 slides we summarize prior reports of smartphone-based pupillography and pupillometry and contrast differences among them regarding the type of illumination sources and cameras they used, the additional software and hardware they used if any, and the aim of pupillography in each report. The advantages of our novel smartphone pupillography device include, it's small, or actually pocket size, in that it does not require an external power supply, as it powers directly from the smartphone, which enhances its portability. The quality of output pupillography media is excellent across the range of illumination and iris colors, and pupillary size measurements are highly accurate and reproducible. And unlike commercially available portable infrared pupillographers, Simultaneous recording of pupillary reactions from both eyes provided by this device maximizes its ophthalmologic and neuro-ophthalmologic clinical value. Limitations of our current prototype include a lack of real-time automated analysis. Although pupillary measurements are not entirely automated, our custom-designed application allows user-friendly immediate post-capture, semi-automated measurements. This pilot study demonstrated the feasibility of smartphone-based infrared pupillography for high-quality photo and video documentation of pupillary examination at the bedside and in the clinic with accurate and reproducible measurements of the pupillary size across different illumination conditions. Here are our references, and thank you again for sticking with us till the end.